Okay, let's see. Let's get this show on the road. Alright. We are continuing our adventure into the world of Lambda calculus. Last we left off, we figured out how to do addition with the transform function that we used for getting the predecessor function. Now, if you forget, excuse me, I recently just had dinner. The add function looks like this, and I can explain it real quick. So n trans. Oh no, my computer seems to be crashing. So this means we're going to perform the transform function n number of times. Okay. So that means if we then have n trans onto, you know, the starting list that we need so we can, you know, do stuff. What this means is it's going to basically add 1 m times, and then it's going to add 1 n times to that, which means we're going to get n plus m. So say n was 2 and m was 3. Run that. You can see that we have 4, 5. 5 is the result that we want. So to get that value out of the pair, we do CDR to get the second value. So we get 5. So that's pretty simple. So let's add that to our list of functions for use of programming. So add takes in a number, and an m, I should say, and then we do CDR. I want to be lazy, so what I'm going to do is I'm actually going to make this function a little different. I'm going to have it take in an f and then m and n, and I'll show you what I'm doing in a second. So it's going to look just the same. mf of n of f of con 0, 0. And this looks almost the same, but you're like, where's the transform function? Well, I'm putting it right here. So when we run this, it's going to put this function as give this function the value f, which is the function that we will use, which is the transform function. CRP, the successor of the second value of the old list. Okay. Oh, I forgot my music. Let's see. Okay. Huh. One sec. Is it just not going through? Ho-ho! God damn it. It's all pain. Oh, why do I have to be so lame and want music? Oh. Do excuse me. Oh, fucking hell. So it's player. Oh. Very sad. Why is that just not doing... Don't tell me I have to do like a soft reboot, right? That would be gay. No, I don't want to... Oh. Oh boy, I'm just falling apart. I'm just falling apart. Yeah. Yes. Yes, queen. It's so strange. Fuck it. Apparently, I'm just not gonna have any music. Which is really lame. That just makes me sad. Wow, okay, so it's all just not working. Oh, whatever. Okay. I'll just, oh, fuck, oh, I know. Please hold. Because I gotta have music one way or another, otherwise I'm gonna lose my fucking mind. Yeah, let's download them. No, none of them. the fuck? Okay. Okay.
Okay.
We good? Hey. Okay. Sorry about that. I had to reset some bullshit on my ends because I decided to do a reboot. I decided to kick out the good stuff. Anyways, where were we? We're doing something. Set the text. Okay. So we just did addition. So now the natural thing is to ask, how would we do subtraction, right? Well, so right, because this is not gonna do anything. Okay. So this is how we do subtraction. Let me show you. Let me teach you a thing. So what we need to do is, subtracting 5 from 10 is the same as applying the predecessor function to the value 10 times, right? Yeah, so that's, look, so if I had, this is 5 and this is 2, this is 5 minus 2, that's 3. So an easy way where you can do this is just say subtraction, we take an n and an m, and then we do, so it's m predecessor of n. So for example, subtract 5 from 10, you get 5. Or, let's say we want to subtract 2 from 5, and I fucked it up. God damn it. I'm a failure. There we go. There. Subtraction. That's actually pretty easy, right? So let's add that to the file. And if you don't understand yet, sorry, I was having a singing match with myself. Since numbers are represented as applying some function onto some value x a given number of times, like this would be 2 because we use f on the value x 2 times. What we can abuse that fact by doing something like say I wanted to subtract something 3 times, right? I wanted to do 3 for 3 times. I want to subtract 2 for some reason. Okay, I can do that, and I can do 15. So I'm going to subtract 2 from 15 3 times. If I'm not dumb. Oh well, I'm a dum dum, but we could do something more interesting, like, well, not more interesting, but, you know, use the successor function 3 times on 0, which will give us 3, right? Because if you add 3, if we add 1 to 0 3 times, we'll get 3 back. And this is going to be true for any number that we define. So that's just sort of a clarification there. Now you might be asking yourself, Alistair, how do I do multiplication? Now, Mr. Multiplication actually is not that hard, if I remember correctly. No, it's not. If I remember correctly, say we want to multiply 2 and 3 to get 6. I do 2, and what we're going to be doing is the thing we're going to be doing 2 times is adding 3, and the value that we're going to be starting off with is 0. So it should give us 6. If I load in the program and all of its built-in functions. Now if I do this, there you go, 6. Why does this work like this? Well, if we look at just add 3, we take a gander at it, if you will, this looks like a whole bunch of gibberish. But to explain it in English, since we know that functions, if I have a function like x and y, and I just return x and y, and I just give it 1, like so, it's going to return a function where it wants a y, and in the body, instead of there being an x, there's a 1 and then a y. So if there isn't enough arguments given, it returns a function to get the remaining arguments, right? So this is what's happening with the add function. Since we're saying we want to add, we're just doing add 3, and we don't have an a final value for the last argument, it's going to add 3 to whatever we get next. So this is we could take advantage of this for making an add 1 function if we wanted. So an add 1 function would be a function that's just add 1 onto something. So add 1 onto 2, that's 3. Add 1 onto 3, that's 4, right? It's pretty simple. But since we're saying, hey, the function that we're going to be applying, so in this case, add 3, since we're saying we're going to add 3 to some value 2 times. The value that we're going to be adding to is 0. So it's going to add 3 to 0, which is 3, and then add 3 one more time to 3, which is 6, giving us 6. So 2 times 3 is 6. Or, you know, I could change this, so it's 2 times 6, which would give me that. That's 10, that's 11, that's 12. Look, I had to say 12 is the successor of 10. If I do that again, we'll say it's 12, right? Bam. Quick maths. So that's how you do multiplication. Pretty easy, right? Now, before we get into division, and this one took me forever to figure out, and I didn't figure it out on my own. I had to wrangle around. Before we get into division, we're going to have to talk about Booleans again, and we're going to have to talk about relational operators, because that's going to be very, how do you say, vital to doing this whole thing, and we're already close on the way. So what we're gonna do is we're gonna make a series of relational operators appear. The first thing we're going to do is we're going to define less than or equal to, otherwise known as lec, as I like to call it as an abbreviation. It's less than, LE is less than, or equal to, that's why there's the Q. Less than or equal to. Oh, actually, we're going to have to backstep even more. We have to figure out if a number is 0 or not. I think you can do that with, I think it's something like this. Crap, I need to load everything in. Yeah. And if I give it 1, it should be false. Yeah, there we go. Well, that was easy to remember. This one is a little bit more black magic to me. All I know is if you give it some natural number and you make that number choose between a function that takes one argument and returns false and just true, it will only give you true if your number is 0. Well, I understand why it returns true when it's 0, because 0, if we look up here, if you look at 0, it looks a lot like how false is defined. And in actuality, if I jump back in here, and I make false choose between the Boolean true and false, false will return false. True with true and false will return true. Right? True chooses true. But now, if I use 0, 0 takes a function, f, and a value, x, and returns x. But it doesn't really, there's nothing distinguishing the two. So it's just going to take true and false and return false. Okay, so when 0 is true, and it gets placed in this expression, it's going to take in this function and this value. And since it's false, it's going to return true only if it's false. So there's that. Yeah. Oh, and then, whatever. So, yeah. So that's that. So let's add that. We're going to call that operation 0, and that's going to return true or false depending on if our number is 0. Neat. Now, how do we tell if how do we tell if x is less than or equal to y? At first, it seems a little crazy, but this all lies in how we do subtraction. So, you might be wondering, Alistair, what happens if I subtract 3 and 4? Because in the regular world, I would get -1. But since we can't go any farther than 0, it just stops at 0. Okay? So one way to check if x is less than or equal to y, because another way that we can get 0 is if both values are equal to each other, like that. So we can say x is less than or equal to y if when subtracting x and y, oh, I don't care if a new version of Microsoft Mouse is available. You can go sleep in a hole alone. We can tell if two numbers we can tell if x is less than or equal to y if when we subtract x and y, the result is 0. And this looks eerily like, you know, some code. We just need to change this and change this to this, change that to the operator sub, wrap this all in a function, take an x and a y, and we just call that equal for less than or equal. Wasn't that easy? So you can ask, is 3 less than or equal to 4? This is true because 3 is less than 4. Is 3 less than or equal to 3? This is true. But is 4 less than or equal to 3? No. So now that we have that operator, let's quickly add that real quick. Now, real quick, we're gonna have to let's real quick add the like 3 simple Boolean operators. Let's go over what those are. Let's open Python for this, okay, or something. Yeah, let's do Python. So we want to do and or and not. So not on some function, on some Boolean, so not false returns true, and not true returns false. So it just returns the opposite Boolean. If I type it right. Okay, and only returns true if both values are true. And it's not in prefix notation. Excuse me, I've been programming too much in Lambda calculus. There you go. But if one of them is false, it will return false. Another one is or. It will return true if either value is true or if both are true. But will return false if both are false. So for not, it's actually pretty easy. Say I had true. If I wanted to make true, to pick between the inverse of it, I would just say, okay, if it's true, make it pick false, otherwise it's going to pick true. So since true is true, it's going to pick the first value out of true and false, so it's going to pick false. If I load all of the library, god darn it, there you go. And if it's false, it will return true. Let's take a look at that. There you go. Isn't that neat? So let's do not. So not on some Boolean is that Boolean where it chooses between true and false. So not true is true because I'm dumb and I did it wrong. And I'm still dumb because, god, kill me. There. Not true, false. Not false, true. Look at that, that's pretty interesting. Now, we're going to do or. So we can say if x is true, so x is a Boolean. If x is a true, it's going to return true. Otherwise, y also is a Boolean. We can just return whatever y is. So that means if y is false and x is false, it will return false. But if x is false, it will return y. And if y is true in this case, it will be true. So let's prove that. False, true, and let's say true. Since x is false, it's going to pick the second value, which is y, which is true. So in this case, it will return true. if false, true, false. X is false, so return the second value, which is this, which is also false, so return false. So let's look at that. Or A and B. A will choose between true and B. So or true, true. This is true. Or true, false. This is also true. Or false, true. This is also true. And or false, false, which is false. Now, we need and. So we need to say, if X is a Boolean, it needs to pick between two values. If it's false, we just are going to outright return false. So I guess in that case, if it's true, it needs to return whatever Y is. So if Y is true, then we'll return true. If it's false, then we return false. So and false, false, that's false. And true, and false, true, false. And true, false, also false. And true and true, that's true. So let's real quick add those Boolean operators. There we go. So we have those Boolean operators. Now, back to relational operators. We have less than or equal to. Now, if we think about it, the only time in which it returns false, so like 0, 0, is when the first value is greater than the second value. Which means if we did not, and then say this, what we have is something that checks if the first value is greater than the second value. So this says is 2 greater than 0. But is 0 greater than 0? No, that works. So that's how we define greater than. It's pretty simple. You just N and M, you apply not onto the result of less than or equal to N and M. So is 4 greater than 5? No. Is 5 greater than 2? Is 5 greater than 5? No, it is not. Neato. So let's add that real quick. Now, we want to figure out how to do less than, you know, is x less than y, right? But when you really think about it, the question is x less than y is the same question as asking is y greater than x, right? Because in both cases, it would, if x is less than y, then that also means y is greater than x, right? So that means basically the same thing. So less than, we can just switch the positions, right? We can say, is y greater than x? Because that's basically the same question. And you can see that this will work. Is 3 less than 4? Yes, it is. But, oh man, is 4 less than 10? Oh no, is 4 less than 1? That's false. Nice. So let's add that as well. Okay. Now, how would we do equal? What makes two values equal? Like, what makes 5 equal to 5? Well, if, besides me saying, well, they're the same value, I can say, well, 5 is not going to be greater than 5. This will be false. And 5 isn't going to be less than 5. This is also going to be false. Okay. So we can say that two values are equal when they are when x is not greater than y, 2, and when x is not less than y. And that's 4. And so if this condition is true, if they're equal, we will turn the Boolean true. Otherwise, we'll return false, if I can spell. So let's see how this works. Is 0 equal to 0? True. Is 1 equal to 2? That's false. Is 2 equal to 2? Is 10 equal to 5? Look at that. We have equal to. And for the hell of it, how about we add greater than or equal to? Okay? And this one should be pretty easy now. We just say that two numbers, here, we can do it in the REPL, I guess. We can say that two numbers are the first number is greater than or equal to the other number if, this is an or. If, let's make this as a function because I'm lame. X, Y. Two numbers, x is greater than or equal to y if either x is equal to y or x is greater than y. So if it's true, we return true, otherwise we return false. So now we have the function, we're going to call it get for greater than or equal to. So is 4 greater than or equal to 4? This is true. Is 4 greater than or equal to 3? True. Bam. Wham, bam, thank you, ma'am. We have all the relational operators that we need. Cool. So, now, division. We have finally made it. How do we do division? How do we do it? Alistair. What even is division? I'm so confused. Well, the rules for division are quite simple, actually. So what you do for dividing two numbers, take an x and a y, and what you should return, so you should return 0 if not if x is no, we should return x. No, we should return 0 if x is less than or equal to 0, less than y. Okay. Because if it's not less than y, so that means it's greater than or equal to y, we want to subtract y. So otherwise what we're going to do is we're going to return +1 on an expression. And the expression is going to be, we're going to divide the x minus y divided by y. But I'm lame, so I did that wrong. So call the div function. Oh, I can remove some parentheses. Okay. So divide x minus y by y and add 1 to the result. So for example, divide 10 by 5 is 2. Divide 10 by 2 is 5. Seems pretty legit. Divide 9 by 3 is 3. Cool. So let's implement this. So, to divide two numbers, A and B. So, if okay, actually, I need to talk about something. No, I'll get there. I'm gonna write this wrong on purpose. So, if A is less than B, then we return 0. No problem. Otherwise, we're just going to have in parentheses the expression, take the successor of dividing, subtracting A from B, and dividing that by B. So this is going to give us a problem. Oh, and just so you know, we're cheating recursion here. So, since in the lambda calculus, like, words like suck for successor and 0, they're names. They don't really mean anything. So, if I have these names in a function and assign it to a variable, I can use that variable name to get the function. So I can basically do recursion. So that's kind of neat. This is going to give me an error and my whole thing is going to explode. So if I try to divide 10 and 2 by 2, it gives me a memory error. Why is that? Let me show you. So what it's saying is, hey, what we're gonna do is, no, that's not a D. So to divide something, divide A and B, what we're gonna do is, so if A is less than B, we return 0 because we're done. Otherwise, I should do it in a different way. We return 0 if A is less than B. Otherwise, we're just going to divide yep. Right, so this is kind of what it looks like. The problem is this is an expression. So before it figures out, what value it should return, out of these two, it tries to evaluate this expression. And since, as I said, we use recursion by calling the div function, which is referenced here, this isn't going to ever end. So how do we stop it? How do we stop it from trying to evaluate this value right here? We can stop it from evaluating it by wrapping it inside of something called a thunk. What is a thunk? You might be asking yourself. A thunk, and this is supported in my language, my version of the lambda calculus, it's the lambda sign and then just a period. Okay? And then we do div subtract A and B and divide that by B. So you're saying, okay, so you're thinking, wait a minute, this is a function, but where are all the arguments, right? Don't they need arguments? Technically, no. And now, I'm giving you a pro tip in case you're using my interpreter. So, the only time, I'm going to use a new thing. So imagine line paper. Oh, that is bad line paper. Can I, is there a thing? No? Oh, that's a bad line. Ooh, this is gonna bug me. This is like lined paper. So remember, the only time we try to evaluate some function like lambda x dot x is when it's on the absolute leftmost part of the function of God, I'm having a problem here. Huh. Because it only evaluates functions when it is on the far left of the imaginary line of paper. If you have something like a thunk, which takes 0 arguments, and say it just returns 0, what'll happen in this case, it'll evaluate it, and then this function that takes 0 arguments, returns 0, gets looked at. And it goes, oh, it has 0 arguments. So strip off the head and the end parentheses, and return this expression, which will get evaluated, which is, in this case, 0. So it keeps it from evaluating an expression right away. Let me give you an example of that. So what I can do is I can make a odd function. No, I can't. So assume we have a odd number. I mean an even number. Okay. So it's gonna take some number, and no, I can't do anything. Fine. So we'll just do some really trivial example. If our number is equal to 0, what we will return is 0. Otherwise, maybe we want to delay some execution. We don't, you usually want to try to do as less computation, scave off, keep from doing as much work as possible, right? So instead of, saying the other value that we'll return is the predecessor of n, right? Which this will work, right? If I give it 5, it'll return me 4. If I load the frickin' module, oh my god, my life's falling apart. Let's do that again. See, it returns 4. But, if I give it 0, it's still calculating what the predecessor of 0 is. And if this is a really complicated function, that's using precious time, calculating what the predecessor of n is. So to save time and resources, I can say, instead, we'll return a function, a thunk, function that takes 0 arguments, and is this expression. So if I do that, you see it works the same way, and if I give it 5, it still gives me 4. Now let's see what's going on under the hood. Actually, we want... Here, I'm gonna simplify this function even more. 0 and... yeah. Okay. So debug mode is on. If I give it 0, you can see all the steps. So 0, this is the expression. We start evaluating the expression. We need to check what 0 of 0 is. It runs through it and figures out that the value we gave in is 0. So then it says, okay, choose between the number 0 and this thunk. It goes through it and it returns 0. But if I give it 1, so if I go up here, this is all the stuff that had to run when n was 0. Right? That's pretty short. this is all the stuff that ran to figure out if it's 0 and then subtract 1 from it. You could see significantly less steps to figure out that it's just 0 and return 0. But if I had it the other way, where I didn't have this thunk right here, and it was just in parentheses, it would always calculate the predecessor of n and have a lot more steps. Granted, you know, it might be negligible because the predecessor of 0 is going to be probably easy to figure out. But so there will be a lot of steps all the time, no matter what. Which is kind of not great when you can reduce it significantly to, oh, what is that? Just like 1, 2, 3, 4, 5, 6, 7, 8, 9 steps? That's so small. So we wrap stuff into thunks. So this is a thunk. Okay. A thunk, again, function that takes no arguments. So it's a forward slash and then a period. And then some expression like mul 2 and 2, right? The whole thing here is this basically needs to be invoked, be it by some value on the right of it, which will give us a weird thing, or by just going, you know, what is this value? Then it evaluates it. So I just forced execution by using the identity function. This is the identity function. Okay. So otherwise, if I just said, you know, hey, here's this thunk, it wouldn't have executed it. But if I prefix it with the identity function, forces execution and executes it. Anyways, so yeah, it's a thunk. Right, why was I talking about? I was talking about because of division. Right, I remember. Okay, so let's do division again. So divide two numbers. Now that we know about thunks, A and B. If A is less than B, then we turn 0. Otherwise, we turn a thunk that'll take the successor of dividing A subtracted by B, which is divided by B. So we're basically going to count up from 0 to get the factor. Oh, okay, there we go. Whatever. So this successor function is really important because at some point in time, it's going to become less than B and return 0. At which point it's going to exit out, and you know it's going to be the successor of 0, which is 1, and blah blah blah. So it's going to have the successor. It's going to increment 0 up to the factor of A when divided by B. You know. So let's try it out. 10 divided by 5. I should have loaded the library. I'm so dumb. Okay, here we go. Take 2. Look, 10 divided by 5 is 2. 10 divided by 2 is 5. Look at that, we have division now. Divide 9 by 2. It's 4. So keep in mind these are all, you know, whole numbers and natural numbers, so we're not going to get decimals or negatives or anything like that. But cool thing, if I try to divide 0 by 0, this is going to run on forever. So how can we fix that? Well, we can change it so the actual division function starts with an underscore, and then the function called div, which takes an A and a B, it first makes sure that both numbers are not 0. So if A is 0 and b is 0, in this case, we're going to return 0. Otherwise, we return a thunk that will divide the actual numbers. So divide 0 by 0, that's 0. Divide 10 by 0. This will also run forever. Yeah, so I need to change this to an OR. Okay. 0. So 10, 0, this is still 0. 0 by 10, that's 0. Great, so now we have division. Let's add it in. That wasn't too hard. So div and b, if a is less than b, return 0. Otherwise, we want to return a thunk that takes a successor of dividing the two numbers. Yep. Of dividing the two numbers, where a is a minus b, and we divide that by b, and that, so that is, so if either is 0, then we return 0. Otherwise, we return a func that actually divides the two numbers. Cool. Now we have division. That's pretty sweet, dude. Now, I guess I'll show one more thing, and that's to show off how to implement mod. If you don't know what mod is, it returns the remainder of a division. So, for example, 9 mod 3 is 0. But 4 mod 3 is 1. So hopefully you've done some long division, so you understand this sort of thing. So if I have 3, so 4 divided by 3, what's the closest thing that I can multiply 3 by to get me as close as I can get to 4? Well, that's 1. So multiply 3 by 1, that'll give me 3. Subtract the 2, and that'll give me 1. So my remainder is 1. So I get 1.1. Right, and I think that's right. Right, so 4 divided by 3 is 1.333. Okay, well, you know what? You can go, or you can go eat my ham. Whatever, it's this bit. This bit. Right, returns the remainder. Okay. So actually, I know a good algorithm for this. And the only reason I know this algorithm is both because I looked it up and because I've done some programming on AppleSoft Basic, and it doesn't have a built-in mod operator, so you have to make your own. So I know for a fact to a mod, we usually use % for mod. A mod b is the same as doing a subtracted by the integer conversion. Well, I should, no, whatever. Yeah, convert a divided by b multiplied by b. Okay? So if b is a factor of a, the result will be 0. Otherwise, it will be some actual number, okay? So that's a really easy thing to see. So if you want to know if some number is even, or if it's divisible by 2, just do n mod 2, and if it's equal to 0, you know that 2 is a factor of n. Anyways, so you might be wondering, Alistair, how does this work? And I actually just recently actually thought about it. So if we have, so say we're doing 9 mod 3, right? So the result of this, by the way, is 0. But to set this up, I'm going to use a little bit of math. So I'm going to do this, and I'm just going to write this out as a proper bit of algebra. So this is a over b, and then we multiply that by b. Okay? Now here's the trick. Okay? Here's the wicked cool trick. So, if I'm gonna isolate it actually. I'm not gonna worry about u right now. Let's focus on this bit right here. And that's a over b times b. Okay? Now, for those of you who are smart children, you'll know that this is an inverse operation. A over b times b is just going to be a, because these cancel out. But the whole thing about this is, these will only properly cancel out and give you a if b is a okay. So I'm getting this wrong because I'm a dumb screwhead. Okay, so I need to be official about this. I'm not a dumb. Well, I am a dumb screwhead, but you know, I like to think I'm not a dumb screwhead. So let's focus on this bit. So if a and b are integers, right? Whole numbers, and in this case natural numbers, so 0 up, then that means b, this will only cancel out and give you back a if b is a integer factor of a. Okay, so for example, 9 over 3. Well, that's just 3. So what we get is 3 times 3, because this is still b, which gives you back 9. And since we subtract a by this expression, if b is a... Here, I'll do some steps. Given that b is a integer factor of a, these will cancel out, and what you'll get is a minus a, otherwise known as 0, right? Because they cancel out. Bam! Simple math. Otherwise, let's try doing, oh, I don't know. Say I was trying to do 9 mod 2. Okay? So this would be 9 minus, convert this into an integer, 9 over 2 times 2. Now, because I'm lazy, I'm going to do 9 over 2. And that's going to be, when converted into an int, that's going to be 4. Okay, so this is going to be 9 minus 4 times 2. Remember, we lop off the remainder of 5 because we are dealing with only whole numbers. So this gives you 9 minus 8. So the remainder of the division is 1. So you can see the only time that you'll get 0 is when when b is a factor of a. So you'll only get 0 when b is a factor of when b is a factor of a, excuse me. So after my small mathematics lesson, this is actually pretty easy to implement. So we take two numbers, a and b. We're going to subtract the result from a. This thing we're subtracting is multiplying some expression by b. That expression being dividing a by b. And that's it. That's mod. That should work perfectly now. So let's take this out for a spin. So if I load in all my good crap, I do mod 9.3. You can see I get back 0. So 3 is a factor of 9. Or 9 mod 2. This should be 1. Indeed it is. So mod works, which is great because I can now check if, say, is 2 a factor of 4, and it tells me it is. So I could, if I really wanted to, say is factor. So if so and say is I should reformat that. So I'm asking, is 2 a factor of 4? This is true. Is 3 a factor of 9? This is true. Now I can do stuff like that. Bam. Simple math. But look at it. I have done so much. And now I can do all sorts of really cool things. If I really wanted to. Okay. And with all this, you can make actually negative numbers. And I've done that. Buddy. Boy. Brohamio. Yeah, but lambda calculus, at first you look at it and you're like, oh god, this is the worst thing in the world, it's super useless, I can't do anything with it. But I hope that in these 2 videos, I've shown you that it is really one of the most versatile languages, and obviously the best language. The best language to do any sort of programming in. And because I'm a total narcissist, let me show you the built-ins file. So I have negative numbers defined in this. So if I load it in, I have negative numbers. And I have a show int thing. So if I show the integer 3, that looks like that. If I can make a negative integer with neg int, and it shows negative 3, so that's pretty sweet. And there's all sorts of cool things. I have division, I think. So negative 10 divided by 5. I should... That's negative 2. So that would be show in so if we multiply negative if we multiply 5 and we use 2, we should get negative 10. And we get negative 10. Look at that. Isn't that pretty sweet? And yeah, it's just a whole thing. I haven't updated GitHub with all this stuff because I'm still working on some cool things. And as you can see, it gets a little complicated when I start working with integers. Tad bit more complicated, and I made some other functions like getting list indexing and getting the last thing in a file and making ranges. I'm currently working on modulus, so the mod operator, but for integers. And I learned that integers have weird, wacky rules for negative mod and all sorts of fun crap that I have to deal with. So wish me luck. I hope you enjoyed this. I don't think anyone is watching even. I think it's just me. Yeah, I'm pretty sure it's just me. But you know what? If you're in the future and you thought this was interesting, leave a comment. If you have any suggestions on some things you think I should do, or if you have any ideas on things you'd like to see me program or live stream about, do leave comments. Talk to me. Alright, well, I'm gonna die probably. I'll see you guys later. I hope you guys have a good evening. And I hope that I blew your mind with some Lambda calculus, yo. Oh, and one last thing. The cool thing about Lambda calculus, before I leave, and cool is a relative term in this opinion, is that you can basically write programs and run them by hand on pen and paper, because the rules are so simple. Yeah. Just think about that one. Anyways, see ya, yo. Have a good one.